Okay. All right. So in this chapter, this is a very important chapter. We'll study oscillations. Okay. So come on. All right. There you go. Can you see the oscillations?
Yes.
Okay. So this is the basic kind of thing we want to study. Okay. So you'll study many important things. So for instance, do you guys know why you take differential equations? Okay. So you will study systems like this that are dynamically changing. And if you want to come up with a mathematical model for this, more often than not, it's the behavior of this system is described by a differential equation. Okay? And the solution to the differential equation gives you the location of this object as a function of time. Okay? So this is an oscillating system. Okay? We will study this system, okay, in detail. So right now, you see there is no damping in the system. Okay? So for instance, one of the things we'll be interested in is this motion looks fairly complicated. Okay? Now we will be able to make statements like so we would want to make statements like, is there something that is constant in this motion? Okay? And it turns out, look at this, the total energy is constant. Okay? So spring potential energy plus gravitational potential energy plus kinetic energy, you see that's constant. Okay? All right. So what we are interested in is the following. So for this system, so again, I'll switch apps and we'll cross our fingers. Come on. Oh, lordy. This is crazy. What's that? What's that? So as soon as I switch app for a second, when there's no signal going, it's switching to HDMI 2, for instance.
You switched it to HDMI 2. Yeah, it's weird. So when you try to cycle back to HDMI 1, at first it goes to HDMI 2, and then it stops. So like when you're on HDMI 2, it cycles through all the different ones and then goes back to HDMI 1. When you do that when you're on HDMI 1, it just goes to HDMI 2 and then doesn't cycle back to HDMI 1. Okay, that's what's going on.
All right. So you saw the app. If I don't get to go back and forth, it's sort of like I'm handicapped. Yeah. So here's what we are interested in. Okay. So you saw that this was oscillating. Okay. So this was an oscillating system. It was going back and forth. Let's say this is the equilibrium position, and we measure the position of this guy as a function of time. The position of the mass as a function of time. Okay. Now, what you're interested in is a complete description of the motion. So you want its position as a function of time. Okay. Now, the configuration of this system is mathematically modeled. Okay, so it turns out, and we'll show this to you in a second, that the position is mathematically modeled by this equation. Okay. When you want to come up with a mathematical model for the behavior of the system, okay, it turns out that this is the equation. So no matter what you do to the spring, all possible motions satisfy this differential equation. Okay? So it turns out that differential equations mathematical model the behavior of a whole bunch of systems. And that's why you study these differential equations. Yeah. All right, so now without going into the app, I'll show you something. All right, so we will study this oscillating system. We'll study this oscillating system. So here's a heavy disk hung by a metal wire. And if you twist this disk, it'll oscillate back and forth. Okay? And so this angle, theta, as a function of time, satisfies the same differential equation. Okay? So the behavior of this system is described by is modeled by the exact same differential equation. Did you guys understand that? Okay. Here is another system, a simple pendulum, a heavy object hung by a string, and if you displace it, it'll oscillate back and forth like that. Okay. And if you measure its position by this angle, and that variable also satisfies the same differential equation. Okay. In each equation, the omega is different, but it satisfies the same differential equation. Okay. And here's a very different looking system. Okay. Okay. A heavy irregular object is suspended from that point, and if you disturb it from its equilibrium position, this will oscillate like that. Okay? And again, if theta is a function of time, satisfies the same differential equation. All right, so what we are going to study is we're going to study oscillations, and we will study a very particular kind of oscillation called a simple harmonic motion. Okay? And that'll show up in all kinds of phenomena. Okay? So here's the basic things you need for an oscillation. So here's the equilibrium position of the system. You disturb the system from its equilibrium position, forces come into play that restore the system to the equilibrium position. So if you pull the spring away from the mass from its equilibrium position, the spring will pull it back. If you compress it, the spring will push it back. Okay? So what is it? What are the forces trying to do? They're trying to restore the system to the equilibrium position. Okay? So for instance, here is another system. Here's a marble in a valley. This is the equilibrium position. You disturb it from there, gravity will bring it back. Okay. Can you think of a system where forces will not bring it back to equilibrium? hill. So you put a marble on a hill, you disturb it from an equilibrium position, it'll run away. This system will not oscillate. This system will oscillate. This system will oscillate. How long will it oscillate? Let's say I pull this aside and let go. It'll keep oscillating. How long will it oscillate? So if there's no friction, it'll oscillate forever. Okay? So that's what we'll start off by doing. We'll consider a system where there's no damping, no friction, and it'll oscillate forever. And then we'll add damping, and then the friction, the oscillations will die down. Okay? So, and you'll see why we'll be interested in that kind of stuff. So for instance, if the wind starts, for tall buildings, if the wind starts making the building oscillate, if the wind starts making a bridge oscillate, you want to kill the oscillations, okay? And so you want to put in damping, okay? So we'll look at all of that. So do you guys understand where we're headed? Okay, so we are going to study systems that oscillate. Okay, again, to make a system oscillate, you need a restoring force, okay? All right, so we are going to study a particular kind of oscillation, a simple harmonic motion, okay? And this kind of motion happens when the restoring force is proportional to the displacement, okay? So for instance, this will be if you have a restoring force like this will be too complicated to analyze, okay? So we're going to study a very simple system like this, okay? And this is applicable in a lot of situations. So the restoring force is proportional to the disturbance, okay? This, of course, is the spring constant in our case, okay? So, and stiffer the spring, bigger this number, and you guys know all of that. You've seen that from labs, okay? So you get a simple harmonic motion when the restoring force is proportional to the displacement, okay? And that's what we're going to study. All right, so you saw in the app, you pull this to the side and this started oscillating. So here's a system whose configuration is changing with time, and it's called a dynamical system, okay? So let's say we denote the position of this mass with xt. What does that mean? This location is changing as a function of time, okay? And what is it that you want to know? You want to know where is this object at all times, okay? Then you have completely solved the motion of an object, okay? So that's what you want to know, okay? And it turns out that if you want to come up with a mathematical model for this, the behavior of this system, here is the equation. And in a second, I'll show you how to come to this equation, but here's a mathematical model for the behavior of this system. And this is a differential equation. Okay. So it turns out that many systems, so you can put a whole bunch of chemicals in a vat and monitor the progress of chemical reactions. That progress can be described by differential equations like that. Okay, there'll be a couple differential equations, but many systems, their behavior can be modeled by differential equations. Okay. All right, so let's derive this model for this guy. This is a simple enough system, so it's an illustrative example. The force on this guy, you saw, is given by Hooke's law. The force on this mass is minus kx. Okay, and again, x is a function of time. Okay, so, but force is mass times acceleration of this object. Mass times acceleration. Acceleration is d square x by dt square, and we'll divide that by mass. So k by m. What is k? Is the spring constant. M is the mass attached. K is positive, m is positive. So to emphasize that fact, we'll write k by m. K by m is always positive. So to emphasize that fact, we'll write that as omega squared. Okay? Because omega, for a real number, omega square is always positive. Okay? So we'll write it like that. Okay? So d square x dt square is minus omega square, and we'll bring that term to the left. So there's the differential equation. Okay. Again, I can't emphasize the importance of this enough. This is a very simple differential equation. Okay. And this equation is describing the behavior of this system that is changing with time. Okay. And if you want, so let's say I pull this guy over here and let go, it'll oscillate like this. I pull this guy over here and give it a little kick, it'll oscillate. It'll be a slightly different motion. But all these different motions are all solutions of this differential equation. Okay. I can take this object, compress it there, and let it go, and it'll oscillate like that. Okay. All those different motions are the solutions to that differential equation. Yeah. How many of you guys are taking differential equation now? Yeah. Just one. All right, so this is sort of a preparation for you guys. So this is sort of a motivation for when you take the course. Okay, so I'll introduce a couple of terms. Okay, what is the highest derivative on this thing in this equation? So the second derivative. So this is a second order differential equation. Okay. Also, so this is d square x dt square plus omega square x. And again, I'm not writing this equal to 0. All right. How about this guy? What order differential equation is this? Third order differential equation. Okay. So that's a third order differential equation. We understand this. Okay, this is a second order differential equation. If this was x squared, that's a nonlinear term. Okay, so every term is linear. So that is linear. This would be non-linear. Okay, that becomes very difficult to solve. Okay, so this is a second order linear differential equation. Okay, did you guys understand that? So second order linear differential equation. All right. So again, what are we interested in? Well, we want to know where the heck the mass is at all times. This is what we want to know. Okay. So what we have to do is we have to solve this differential equation. Okay. Now, solving the differential equation, it's a lot of it is trial and error, but you learn techniques to solve this. Okay. So for this differential equation, we just try various functions, and here's the solution. Somebody came up with the solution, pulled it out of their hat. Okay. So this solution, you see, this, what is this? This is giving you the position of this mass as a function of time. Now let me point out a couple of things in this solution. So xt is cosine omega t plus a cosine omega t plus phi. Omega is there. That guy is there in this original equation. What is this a? A is not anywhere in that equation. Where is phi? Phi is not there in their equation. All right, so if you have an nth order differential equation, the solution will have n constants that have to be determined by initial conditions. Okay. So if this was a third order differential equation, your solution would have 3 constants. Okay. And so, did you guys understand that? So these constants are determined by initial conditions. So what will be the initial conditions? So for instance, I'll pull this over there and let at t equal to 0, the position is 5 meters and the velocity is 0 meters per second. And those will determine those constants. Okay. All right, so that's the general structure. Okay, now that you know this, now that you know where the mass is at all times, you can calculate its velocity and its acceleration, and that's what you're interested in. Okay? So again, what is you have a system, you come up with an equation describing the system. Okay. And the equation generally is a differential equation. Okay. How did you come up with the equation? You put some physics principle in it. Okay. And then you solve the differential equation. And the solution gives you the configuration of the system. The solution is the configuration of the system as a function of time. Okay. And that's what you're interested in. Okay. Okay, so did you guys understand that? Again, it could be a physics principle. So if it's an equation in economics, it's an economics principle. If it's population dynamics in, let's say, biology, it's a biological principle and stuff like that. Okay, so whatever system you're studying, you put in the principle that governs the behavior of that system, and that will lead you to an equation, generally a differential equation. Then you solve the equation, and you get a solution. The solutions are how the system will behave under various conditions. Okay. What are the various conditions? The various conditions are under various initial conditions, A, phi, in this case, A and phi. Okay? All right, any questions on that? Okay, so you saw that the motion of this is given by a sine or a cosine function. Okay? And so this illustrates that indeed this is not just some mathematical trickery. It's indeed the physically correct solution, and you can verify this. Attach a pen to this mass, get it to oscillate, and if you roll this paper at a constant velocity, that'll simulate time, and what you'll get is a plot of a sine or a cosine function. Okay. All right. So you saw that. So here's a mass attached to a spring. Here's the equilibrium position. And then if you pull this mass aside and let it oscillate, it'll oscillate like that. Okay? It'll go back and forth. Going from one extreme spot there and back, that's one oscillation. The time for one oscillation is called the period. And the period is given by 2 pi times m, the mass, divided by the spring constant. Okay. We'll verify this formula. We'll test this formula in lab next week. You know. And let's make sure that this makes sense. Okay. So for a given spring, the more mass of the object you attach, the slower it'll oscillate, the longer it should take to oscillate. Okay, so and that the period formula tells you that the greater the mass for a given spring constant, the greater the period. For a given mass, if you attach a stiffer spring, it should oscillate faster. The period will go down. So for a given mass, if the spring constant is larger, the period will be smaller. Okay. All right, this this is the frequency. The frequency of oscillation is how many times it will oscillate per second. So smaller the period, greater the frequency. Okay. All right, so this one slide summarizes everything we've said so far. Okay. Okay, so what was our system? This was our physical system. So here's the equilibrium position, and you've set this system in motion. Okay, so this system is oscillating. Okay, and the behavior of this system, the dynamical evolution of this system, is governed by this differential equation. Okay, so here's the system. Here's the mathematical model. Okay, and then you came up with the solution. Again, This differential equation was a second order linear differential equation. Okay. Here was the solution, and now you're done. You've completely solved this problem. Okay, why are we doing this? You could study this problem in lab. It would be much harder, and your hands would get dirty. But if you have paper and pencil, you come up with a mathematical model. Solving this is very easy, and now you know the behavior of this system. How do you know you're right? Then you go test it in lab. Okay? And if what your model predicts does not pan out in the lab, then what do you do?
Revise your equation.
I'm sorry?
You revise your equation.
That's right. So there's the process. Okay? Yep.
Does the delta represent acceleration or is it a constant?
Which one? What?
Does the capital delta represent acceleration or is it a constant you have to solve for?
No, that's the amplitude of oscillation. Amplitude is the maximum distance that thing goes. Okay. All right, so here is the position. The velocity of the object at any time is time derivative of the position of the object, and there is the velocity at any time as a function of time. The acceleration of the object is the second time derivative of the position, which is that. Yeah. So once you have the solution, you can calculate other things of interest, which is the velocity and acceleration. Okay. Now, if you look at these expressions, okay, what is the maximum value the velocity can have? See, the maximum value the sine or a cosine function can have is 1. So that'll be 1, and the maximum velocity you can have is plus or minus a omega. Plus when the object is moving to the right, and minus when it's moving to the left. Okay? And it turns out that the maximum velocity will be when the object is at the equilibrium position. Okay, so if you pull it on the side and let go, it'll be going the fastest here. Okay. What is the maximum value for the acceleration? Again, the maximum value will correspond to when this is 1, so it'll be omega square a. So a max will be omega square a. And it'll be plus or minus omega square a, and we'll come to that in a second. Now, be careful answering this. When will the acceleration be maximum?
At the peaks and the troughs.
I'm sorry?
At the top point of when it's on the string, or the bottom point at the peaks and the troughs of the
How about on here, on this diagram?
when it's all the way to the right or all the way to the left.
Right. So the acceleration will be maximum at the extremal points. And you can see that from the following. So the force is given by minus kx, which is equal to mass times acceleration. Okay, so when the force is the greatest, when this is the furthest, that's when the acceleration will be maximum. Okay? So at these points, the acceleration is maximum. At this point, the acceleration is to the left, and it'll be negative. At this point, the acceleration is to the right, and it'll be positive. Okay? So velocity is greatest at the center, and acceleration is greatest at the extremal points. Okay? So you saw that this system oscillates. Again, when does a system oscillate? When there's a restoring force. Okay? A force that is restoring it to the equilibrium position. So this system is oscillating, and you saw that the motion was fairly complicated. And now we want to see if there is something that is constant in this during this motion. And so here was the kinetic energy. Here's the potential energy. Potential energy is 1/2 kx squared, spring potential energy. And you can take these expressions x and v and put it in there. And that's what we've done. And here's something you notice. If you add the two, the kinetic plus potential energy, you see this is constant. The potential energy depends on time, kinetic energy depends on time, but their sum does not depend on time. That's a constant. Okay, that's a constant of motion. The total energy is the same at all times. Okay? So with this is with no damping present. And that's the kind of stuff that we look for. Okay? So for instance, you guys remember in the last chapter, for a planet going around orbiting the sun, in that motion, the speed is changing on an elliptical orbit. But if you were looking for something that was constant, is there anything that you remember that was constant for this motion? No. Angular momentum for the planet was constant. Okay, that was Kepler's second law. Okay. Kepler, of course, didn't state it that way. He said that the planet covers equal areas in equal time intervals. And okay, so again, so in various kinds of motions, we are looking for constants of motion. Yeah. Yeah. All right, what this formula gives you is, okay, so again, you pull this mass to the side, and as it's coming closer to the center, it's going faster and faster, and then it'll slow down and come to a stop here, and then keep repeating that motion. Okay, what this gives you is the velocity of this object as a function of position. Okay, A is the amplitude of the motion, meaning that's the maximum distance you will pull the object was pulled from. Okay, so there's the amplitude, you pulled it there and then let go of it. Okay, and the object goes from here to there and back and forth. Okay? And this formula gives you the speed of the object or the velocity of the object as a function of position. Okay, and this shows you when x equal to 0, that's when the object is in the middle, that's when its velocity is maximum. Okay. When x equal to a, the velocity is 0. So at the extreme position, it's come to rest, and then it'll change directions. Yep. All right, so again, let me review this. Okay, so make sure you guys understand this, because we'll see that everything that we've said here applies to many different systems. Okay, so here's a system that oscillates. What was needed for oscillation? What you needed was, if you disturb the system, what you needed was a restoring force. Okay. So for this system, there's the equilibrium position. You disturb it, and restoring forces come into play. Okay, so if you disturb it and let go and it oscillates, the behavior of this system is described by this mathematical equation. Here's the solution. What is a solution? A solution is a solution that tells you where the object is at all times. And once you have the position of the object as a function of time, the configuration of the system as a function of time, you can calculate other quantities of interest. Okay. So you have system, mathematical model, solution. That's what you're interested in. Okay. All right, now what we'll do is we'll describe other systems, 4 other systems or 3 other systems. It'll turn out that the mathematical model is identical. And so we already have everything else. Okay? And that's what we're going to do. You guys understand? All right, so here's the next system. So we will take this disk, a uniform disk, and suspend it by a wire, and the motion will be, we'll twist it, and it'll oscillate back and forth like that. And the configuration of the system, so okay, this is the equilibrium position, and we'll measure the disturbance theta as a function of time. Okay? And it turns out that again, if there's no friction, the friction will be when the wire twists. If that twist is heating up the wire, then there's friction and you lose energy. But if there's no friction, this will oscillate forever. Yeah? All right. The equation governing the configuration of the system is exactly the same. So d squared theta by dt squared is omega squared theta t. Okay. What is omega in this case? So for this system, omega squared was k by m for the mass attached to the spring. For this system, omega squared is k, omega squared is kappa, which is the torsion constant, divided by I, the moment of inertia. Okay? So this was the spring constant divided by mass. This is the torsion constant divided mass gets replaced by moment of inertia. Remember, linear motion, inertia is mass. For rotational motion, it's moment of inertia. Moment of inertia of this object about that axis. Okay? And so the equation is exactly the same, and we already know the solution to that. Okay, so linear second order differential equation, and here are the two constants that have to be determined by initial conditions. Okay, these two constants are not there in the original equation. Yeah. So what would theta naught be? Theta naught would be the initial angle to which you twist and then let go. Okay, and so on. And this would be the phase constant. So if you twist this and let go, that would be 0. Okay, for t equal to 0, cosine omega t would be 1, and that would be theta naught. Okay, so that's the initial condition there. The period of oscillation is, okay, you just twisted it there, let go, it goes there and back there. The period for oscillation is 2 pi over I divided by kappa. For this system, the period was 2 pi over mass divided by spring constant. Okay. Again, all the formulas are very similar. Mass got replaced by moment of inertia. Spring constant got replaced by torsion constant. Yep. Here's a simple pendulum. Okay. The forces acting on this guy, the two forces acting on this sphere are the force of gravity and the tension in the string. This component of the force is balancing the tension, and this component of gravity is what's restoring it to the equilibrium position. This component is what makes it oscillate back and forth. Again, if you're measuring, the configuration of the system is measured by this angle, theta t, and so the differential equation governing that equation is exactly the same. Okay, d squared theta t divided by dt squared plus omega squared theta t equal to 0. And omega squared in this case is g over L. G is the acceleration due to gravity. L is the length of the pendulum. Okay. Now, this equation is valid under the approximation where sine theta can be approximated to equal to theta. Okay, and this is true for small angles. Okay, so this differential equation would not describe this if you swung the pendulum from there, for instance. Okay, so for only small angle oscillations will this equation work. And small angles we mean by less than 10 degrees. Okay. All right, so again, so here is this oscillating, again, there's a solution to the differential equation. Okay, so this describes the motion of this swinging pendulum. And here are the two constants that are determined by initial conditions again. Okay. The period of this simple pendulum is related to its length. The period is the time for one oscillation. Okay. And this was the first mechanical clock that we came up with. Okay. So you see, you fix the length of the pendulum and the period is fixed, and so you can make a pendulum where the period is 1 second. Okay, so one swing will be 1 second. Okay. And apparently Galileo got this idea. Galileo was the one who invented this. He was sitting, he was at a church sitting at a service, and a small tremor shook the earth, and the chandelier started swinging. And then he used his pulse to time the chandelier. And he realized that even as the amplitude was dying down, the period was constant. Yeah. So that's how come we invented the pendulum clock. Okay, here's a physical pendulum. A simple pendulum is a small, heavy object hanging from a long string. The dimension of this is small compared to the length of the string. So a simple pendulum is a small object hanging from a long string. A physical pendulum is the mass is distributed all over. Okay, so for instance, this object can be a physical pendulum. Okay, this is a physical pendulum. Okay. So here's the center of mass of the object. The equilibrium position would be the center of mass being right below the point of suspension. And if you disturb it from there, this will make it oscillate like that. Yep. And again, so the restoring torque is mg, the weight of this object, and d sine theta is you're calculating the torque about that point. Okay, so there is the moment arm. Okay, so that's what restores it. And again, there is this angle measures the configuration of the system, and theta t solves the same differential equation. D squared theta by dt squared is plus omega square plus omega square theta t equal to 0. And omega square here is mgd by I. Okay. mg is the weight of this object. That's the weight of this object. And d is the distance of the center of mass from the point of suspension. All right. See, so if d is 0, omega is 0. Omega of 0, what does that mean? Frequency is 0, meaning it won't oscillate. And that makes sense. If you suspend it from there, okay, if you pivot it there, that's the only point about which it won't oscillate. Okay, if you turn it, it'll just stay there, and turn it back, it'll stay there. Okay. Yep.
What's the difference between a simple pendulum and a physical pendulum?
So a simple pendulum is a tiny mass hung from a long string. And this dimension is negligible compared to that. That is, the size of this is small compared to the length of the string. A physical pendulum, the mass is spread all over. Yep. All right, so there's the differential equation. Okay, again, here's the period, 2 pi times the moment of inertia of this object about that axis, times mgd divided by mgd. Mg is the weight of this object, d is this distance. Okay. So the period of this physical pendulum is given by that. Okay, now here's an interesting feature. You would think that this is fairly dry, and why are we studying this? Okay, it turns out your leg is a physical pendulum. There's the point of suspension. The center of mass of your leg is somewhere there. You can calculate the period of for this physical pendulum. The period would be, there's half of the oscillation, full oscillation. Calculate the period, and you can calculate your normal walking speed. And it turns out to be exactly that. So you can do this for any animal. Okay. And why is that the normal walking speed? Because that's the least energy speed. Okay. So that's the physical pendulum. All right, so before I go on, so we've studied 4 systems, 4 very different looking systems. Okay. So here was the configuration measured for this system. What was the mathematical model? Okay. So that was the mathematical equation, differential equation describing the behavior of that system. Here was there was the equilibrium position. Same differential equation describing the behavior of this system, and again omega is different for omega is different for each one of them. Here's a simple pendulum. In this case, omega square was k by m. For this case, omega square was kappa over I. For this case, omega square was L by G. Okay. And then physical pendulum. Again, the differential equation was exactly the same. And omega square was mg, this was d, mgd divided by I. Okay, so here's why you take a differential equation course. You have very different systems, and it turns out that all those different systems, the behavior of all those different systems is described by the same differential equations. Okay? So that's what mathematicians do. They'll study equations and study solutions of those equations, and those turn out to be applicable in many real life situations. All right. Any questions before we move on? Did you guys understand that? All right. Everybody is tired. We're almost done. Okay. Now, here's an interesting thing. Okay, so you guys saw that I attach a mass to a spring, pull it to the side, and what happens? It oscillates, the mass oscillates. Okay. Okay, and you saw that it starts off at rest here, speeds up, it's going fastest here, and then it'll start slowing down, and it'll come to a stop here, and then again start speeding up, and so on. Okay, that's how it oscillates back and forth. Now, what we'll do is the following. So let's say whatever is the speed of it at this point, that's where it's going the fastest. We'll take an object and send it at that speed in a circle with the radius being equal to that. Okay, so we'll send an object like that in a circle at that speed and project its shadow on this plane. And the motion of this shadow is exactly equal to that. Did you guys understand that? So, a simple harmonic motion is a projection of a uniform circular motion. You could do the same thing, project one image over here, okay? So it turns out that uniform circular motion is a sum of two simple harmonic motions. Have you guys seen this before? Where?
Well, I've seen something different where they showed the oscillation
Mm-hmm.
in the graph, and they showed the rays of the forces,
Mm-hmm.
and it would go back and forth along kind of like x equals y,
Mm-hmm.
and as the oscillation went back and forth, you could see that the forces would grow as it goes out, and it would shrink, and
Mm-hmm.
the force would kind of go in the opposite
Right.
direction.
Yeah. So, I mean, that's the restoring force being shown. Here's another real life situation we saw it in. Okay, remember we talked about digging a tunnel through the earth? And you'd fall into this tunnel and you would oscillate simple harmonically. And the period of that was exactly the same period as for the International Space Station. Okay? So that's exactly what's happening here. Okay? So a simple harmonic motion is related to uniform circular motion. And this thing shows you, so if you got an object going in a circle at constant speed, here's the x component of the velocity that'll equal exactly the velocity of the spring mass attached to the spring. A uniform circular motion, it has centripetal acceleration, and this component of the acceleration matches the acceleration of the mass attached to the spring. Okay? All right, so now we're ready to do something slightly more complicated. Okay, in real life there is friction, so we're going to add friction. Okay, so for a system where there was no friction, here was the differential equation. For this system, the differential equation xt is that. Okay. Now what we're going to do is, we'll say, what if there is friction? How does the model change? Okay. What is the equation that models the system with friction present? Okay, so here's a simple way to add friction. You take this mass attached to the spring and put it in a glass of water or honey. Okay, if you put it in water, there's less friction. If you put it in honey, there's more friction. Okay, that's the idea. Okay, so we're going to model friction in a simple way like this. Okay, and this, the D representing drag force. Okay, so the faster this thing is moving, the greater the friction. Okay, and that's how we're going to model it. Okay, so the drag force is proportional to the velocity. Okay, now there might be situations where the drag force is proportional to velocity square, and that becomes a nonlinear differential equation, and that becomes very hard to solve. Okay, so we're going to consider the simplest extension to the model. Okay, so the drag force is going to be proportional to the velocity. Okay, and B is the damping coefficient. Okay, so B for honey will be larger than B for water. Okay. All right. So now the net force on this object, this is the spring force, and there's the damping force. Okay. So there is the physics that's gone in. Newton's second law says mass times acceleration is the net force on it, and here are all the forces, spring force and that. Okay. Acceleration is d square x by dt square. There's kx, and velocity is dx by dt. All right. So there's the new differential equation. Okay. What was the differential equation? Without friction, it was m d square x by dt square plus kx equal to 0. Okay. And without friction, when friction was not present, b was 0, and so you get this equation reduces to that. Okay. Now all you've done is, because of friction, you've added this term. Okay. So there is a new differential equation. All right, again, you will learn techniques to solve these equations. Okay. So what are you interested in? What is xt as a function of time? Okay. And here's the solution. Okay. So it's part guessing the solution and part educated guessing. Okay. So without friction, the solution was a cosine omega t plus phi. So this solution is exactly the same, except that the amplitude is exponentially decaying. Amplitude is decaying exponentially. That was the only difference. Okay, so that's what friction does. So it kills the oscillation, and that's what was shown here. So the amplitude of oscillation is dying. Yeah. All right. Well, let me take you back several slides. So we saw that the total energy was constant, that is kinetic plus potential energy was constant. Okay. So if the amplitude is dying, the energy is being removed. Energy is being removed from the system. Okay. And what is happening to that energy? Right, that's what friction does. So mechanical energy is being converted to heat. Okay. And okay. So mechanical energy is being converted to heat, and greater the friction, faster the energy is being converted to heat. Faster the amplitude dies out. Okay. Now this formula also tells you this is the new frequency of oscillation. This would be the frequency of oscillation without friction. Okay. So this is also written like omega naught square. Omega naught is the angular frequency without friction. B or 2m square. Okay. So the new frequency of oscillation is slightly smaller than the frequency of oscillation without friction. Now notice something. If this term was equal to that, then this would be 0. So if there's too much damping, the system won't even oscillate. Okay. Now you might want to do that in systems like this. Let's say you're driving a motorcycle, you hit a pothole, you don't want this motor wheel to be oscillating. You want it to come back and not even oscillate. So you want to put enough damping where it doesn't even oscillate. It comes back and it comes back to the road. Okay? If it oscillates, then it'll bounce. And of course, you don't want it over damped where it doesn't even come back to its original length. Okay? You want the motorcycle wheel to come back to the road. Okay? So when this term is equal to that, that is critical damping and it won't oscillate. When this term is smaller than this, it will oscillate some. And when this term is bigger than that, it won't even come back to its original. That's overdamped. Okay? All right, so what we have done is the following. Okay, so this was a system without friction. Then this was a system with friction present. Okay, now we're going to add one more complication. Now what we're going to do is we're going to push on this. Okay, so we are going to look at forced oscillations. Okay. So if a child is on a swing and the swing has friction, you push it once, what happens? The oscillation dies down. You saw that. And what happens if the oscillation dies down? The child cries. And so you want the child not to cry, so you push. So we're going to consider that. Okay, so we're going to push regularly. Okay. So now the equation, so again, we are experts at mathematical modeling. So we are going to apply a sinusoidal force. This is the driving force. This is the friction force. This is the spring force. So this is the net force. And all we are doing is using Newton's second law. Net force is mass times acceleration. Okay? So this is the sum of all the forces, and there is mass times acceleration. Okay. So the differential equation now is, okay, so I'll write it. So there is the differential equation. If friction was absent, this term would not be there. If you're not pushing, this term would not be there, and you'd get back the original equation. Okay. And again, as you add more and more terms, the solution to the equation gets more and more complicated, but this can be solved. And here's the amplitude. Okay, F naught is the amplitude of the driving force. Yeah. So here is the F naught divided by the mass of the system. Here is the driving frequency. Here is the new frequency of oscillation. So the amplitude of oscillation is the driving frequency minus this, and there's the damping coefficient. Now let's look at this equation, okay, carefully. Okay, let's see what happens to the amplitude. If the driving frequency matches the natural frequency of oscillation, this term will be 0. And if there is very little damping, this term will be close to 0, and this amplitude will blow up. Okay, so when the driving frequency matches the natural frequency, the amplitude grows up. And that phenomenon is called resonance. Okay, and you have to deal with this in many real-life situations. Okay. So let me show you. Did you guys understand that? So when the driving frequency matches a natural frequency and there's very little damping, the amplitude increases dramatically. And if a structure oscillates too much, you can compromise the structure. Okay, so if the amplitude increases too much, and so a lot of civil engineers in large structures, you have to put in damping. Okay, so let me show you a few videos and then. Okay, so here's a bridge in Russia that So when the wind blows, that's the driver. Okay, when the frequency at which the wind is oscillating is matching a natural frequency of the bridge, and the bridge oscillates like that. Okay, so you have to shut down the bridge. And of course, you guys have seen this one.
The day you get your Clear Choice dental implants changes your struggle with missing teeth forever. It changes how you eat, how you feel, and how you enjoy life. It changes your smile, and how others smile at you. Clear Choice Network doctors have changed over 100,000 lives.
So that was a bridge near Seattle, built near Seattle, and it lasted less than a year after it was built. Obviously, they didn't put enough damping in there. Okay, so that's forced oscillations, and let me show you one app before I'll let go of you. Okay, so here's a mass attached to a spring, a typical oscillator, and we are going to grab hold of this and pump energy in there. So that's forcing the oscillator. We are pumping energy at a regular interval. Okay. Now what this is showing you is, so there's the natural frequency, and that point is the frequency of oscillation of the forcing force. Okay. So you're applying a regular. And right now, nothing spectacular is happening. Okay. So what I'm going to do is, okay. So now you see the forcing frequency is matching the natural frequency. And now let's see what happens. Again, the amplitude of oscillation will be the same, so you're still oscillating at the same frequency. The amplitude of the forcing is the same, but look how the system behaves now. So that's what was happening to the bridges and stuff like that. A bridge oscillates at that frequency, of course it's going to break down. Okay? You don't want tall buildings crumbling like this. You don't want every bridge crumbling like that. So you have to put in the appropriate amount of damping. Okay? And so, all right, so resonance can be a scary thing. Are you going to come back? Did it come back?
Yeah.
All right. So resonance can be a scary thing, and this is how come buildings get destroyed. So for instance, in Mexico City, so apparently, so this was back in 1985. The natural frequency of a building depends on its height, okay? And if the ground shakes, and if this frequency matches the natural frequency of a building, it'll collapse. So, so angular frequency of the seismic waves that reached Mexico City were concentrated about 3 radians a second, meaning it was oscillating, the ground was oscillating once in 2 seconds, okay? And matching the natural frequency of many intermediate height buildings. So this guy collapsed and these guys survived. Nowadays we build many tall buildings. This is Burj Khalifa right now, the tallest building. And the top sways about 2 meters. 2 meters is that much. The height of an NBA player. Yeah. So you don't want this thing falling off. This is a building in Philadelphia, and at the top you have a water tank and with baffles, and as the building shakes, this water damps the shaking, the vibration. Yeah. All right, so anyway, you want to make sure you understand resonance. What is resonance? When the driving frequency matches the natural frequency, the amplitude of the oscillation go up. Okay? And that's resonance. And you gotta